Greetings and a very good day. We are from Group 5, and for our group, we will be doing heat powered turbine. Our group members include Hafiz, Hilman, Alia, and Lau. And that concludes our introduction.
So our project focused on the conversion of heat energy into electrical energy using a candle as our heat source. The core of this project is based on the first law of thermodynamics, which governs the transfer and transformation of energy in both closed and open systems. Our primary aim is to demonstrate how the heat generated by a burning candle can be harnessed to produce electrical energy. And this process follows thermodynamic principles where thermal energy is captured and converted into a usable form of energy, which is electricity. And by doing this, we can explore energy conversion and the efficiency of these processes.
So now I will be talking about the thermodynamics concept. So in this project, we are designing a heat-powered turbine that converts thermal or heat energy from a candle into mechanical energy or mechanical work. This follows the first law of thermodynamics, which states that energy cannot be created or destroyed. It is only transferred or converted from one form to another. So the system that we analyze is an open system or control volume, meaning energy and mass flow through it. The energy entering our system is the heat energy from the candle, and the energy leaving the system is in the form of air movement and mechanical work, and the mechanical work is produced by the spinning turbine. Okay, so now this is the energy balance equation for a steady flow control volume. So we cancel out the potential energy because there is no change in height or potential energy. Okay, Q dot is the heat input from the candle, which is assumed to be 80 watts. W dot is the work output, which we observe as the spinning motion of the turbine. M dot is the mass flow rate of air, while H is the specific enthalpy change, showing how much energy is absorbed by the air. And finally, V represents the velocity of the air. Okay, so how does it work? When the candle burns, it hits the surrounding air, which causes the air molecules to expand and rise due to convection. So the rising air flows over the paper turbine. The rising air flows over the aluminium turbine, which we use, transferring some of its energy and causing it to spin. This is an example of heat energy converting into kinetic energy and then into mechanical work. However, not all of the heat from the candle is converted into mechanical output. Some of it is lost to the surrounding as heat, which aligns with the second law of thermodynamics.
Hello, I'm Alia. Today I will be talking about the real-world application of our heat-powered turbine and how similar concept can be used in our practical engineering solution. Our project demonstrates how heat energy can be converted into the mechanical energy using the natural convection, which are the basis of many real-world applications. The first application is passive ventilation and air circulation system. In building, warm air naturally rises, creating airflow without the need of mechanical fan. These principles are usually used in ventilation design for home, greenhouse, and also for industrial building. It is to improve the air circulation and also to reduce the reliance on electricity. Our project demonstrates the same principle, where the heat from the candle create airflow that move our turbine, just like how the temperature differences help move air in ventilation system. Another application is heat-powered water pump, which are commonly used in remote area where the electricity is limited. This pump work by using heat to create pressure differences that allows the move to water from one location to another, similar to our turbine, which relies on rising hot air to generate motion. This pump harness heat to create movement and transfer energy efficiently. They are particularly useful for irrigation, livestock watering, and also emergency water supply system. A more familiar example is the hot air balloon. Just like in our project, where hot air rise and spin the turbine, in a hot air balloon, a burner heats the air inside the balloon, causing it to become lighter than the surrounding, which have a cooler air. This creates lift and also allow the balloon to float. This is the direct example of the same thermodynamic concept that we use in our heat-powered turbine, proving that the simple heat energy can be converted into a useful motion.
To conduct this experiment, we use aluminum foil as our thin metal sheet. Then, using said aluminum foil, we cut it up into a circular spiral to act as our fan blades. And once we are done cutting up the aluminum foil into a circular spiral, we use candles and also chopsticks to complete our setup as shown in the video. Using the foil that we have prepared, carefully place it on top of the chopstick, making sure that it does not pierce nor does it actually uh, fall off of the chopstick itself. Then we carefully, as well, because of HSE, light up the candles at the bottom of the setup. And after a few seconds, the fan blades that we made out of aluminum foil will start to spin. To conduct this
In this
experiment,
experiment, we explore the principles of the first law of thermodynamics through a heat-powered turbine. Our calculations showed a power output of negative 1366 watt, meaning that a significant portion of the heat energy was lost to the surrounding rather than converted into useful work. This highlights inefficiencies in small-scale thermal systems. However, improving heat transfer, turbine designs, and airflow could enhance performance. Despite these losses, the project effectively illustrates energy conservation and transformation in an open system, emphasizing the need for better thermal efficiency in real-world applications.
thank you so much for your time for watching our presentation. I hope everything in this video is clear and easy to understand. Again, thank you.